Now in its 27th year, the school year 2024 to 2025, the Philippine Mathematical Olympiad is the oldest and most reputable nationwide mathematics competition among high school students. After its trial run in 1984, it was officially launched in 1986 and has been held annually since 2007. The country's contestants to the International Mathematical Olympiad are chosen from the top students who compete in the Philippine Mathematical Olympiad. The PMO is a project of the Mathematical Society of the Philippines and the Department of Science and Technology Science Education Institute. Hello, I'm Richard Eden. I help out with the Philippine Mathematical Olympiad and also in the training of the country's contestants to the International Mathematical Olympiad. A good number of problems in the PMO ask for the maximum or the minimum of some given algebraic expression. But what do we mean precisely by maximum or minimum? For example, what is the minimum of x squared? Did you say zero? If yes, you're correct. But why? Well, you might say it's because x squared is greater than or equal to zero for all real numbers x. Okay. But isn't it also true that x squared is greater than or equal to negative 1? So why are we not saying negative 1 is a minimum? Well, it's because x squared is never going to become negative 1 anyway. X squared never attains negative 1 as a value. But what about 0? Well, x squared assumes the value 0 when x is equal to 0. In fact, equality happens, or in other words, x squared is equal to 0 if and only if x is equal to 0. IFF is shorthand for if and only if. It's meant to capture two statements that if x squared is equal to 0, then x is equal to 0. And also that if x is equal to 0, then x squared is equal to 0. In the end, 0 is a minimum, and we're able to identify precisely when x squared assumes the value 0. So in general, the minimum of an expression is the smallest value it can attain, while the maximum is the largest value it can attain. The minimum and the maximum are respectively the smallest possible value and the largest possible value of that expression. Today, we'll present a useful tool for finding the maximum or minimum of certain expressions. It's based on the fact that the square of any real number is greater than or equal to 0. In particular, let's take the square root of a minus the square root of b. We require a and b to be non-negative so that we can take their square roots. We can expand the square on the left and then rearrange expressions as follows. The left side, a plus b over 2, we call that the arithmetic mean of a and b. Yes, the AM is the average of these two numbers. The right side, the square root of AB, is called the geometric mean of A and B. This general statement is a special instance of what we call the arithmetic mean geometric mean or AM-GM inequality, that the arithmetic mean of A and B is greater than or equal to their geometric mean. Let's not forget the assumption that A and B must be non-negative. And furthermore, we can identify precisely when equality occurs. From the first line, the square is 0 if and only if the square root of a minus the square root of b is equal to 0. But hey, that means a is equal to b. So, in other words, the AM equals the GM if and only if a is equal to b. The AM-GM inequality can be used in many different ways. One way is this. Say we know something about the product AB, then the inequality can tell us something about the minimum of a plus b. Or if we know something about, say, the value of the sum a plus b, then the statement can give us the maximum of the product AB. Here's an illustration. Find the smallest possible sum of a positive number and its reciprocal. If we let x be the positive number, then we want the minimum of x plus 1 over x. Note that this is a sum, so we can use the AM-GM inequality here for your reference. where the two numbers a and b are going to be replaced by x and 1 over x. On the left side, the larger side, that's half the sum. On the right side, which is the smaller side, the geometric mean would be the square root of x times 1 over x. Fortunately, no matter what x is, this product is 1, whose square root is 1, which means that the sum of any positive number x and its reciprocal is greater than or equal to 2. So the answer is 2. But wait, is 2 actually attained? Well, equality in the AM-GM inequality occurs when the two numbers we considered, x and 1 over x, are equal, which means, of course, x squared is equal to 1, but x is positive. So, yeah, that happens when x is equal to 1. And you can confirm 1 and its reciprocal, also 1, have a sum equal to 2. Now, this problem is from the qualifying stage of the 25th Philippine Math Olympiad. For positive real numbers a and b, the minimum value of 18a plus 1 over 3b, that's the first factor, second factor 3b plus 1 over 8a, can be expressed as m over n, where m and n are relatively prime positive integers. The value of m plus n is, then we have four choices to choose from. This really is a problem where we have to find the minimum of the given product. Now, each of the letters A and B occurs in the main level and also in the denominator. So the purple terms, which are the A terms, have a product of 9 over 4. The gold terms, which are the B terms, have a product equal to 1. But we know that's not yet the end of the multiplication. There are two other terms, 54AB and 1 over 24AB. Observe that if we are going to multiply these two black terms, the ABs would cancel. So something nice is going to come out of multiplying them. So let's use the AM-GM inequality. The arithmetic mean is greater than or equal to the geometric mean. Of the two numbers, 54AB and 1 over 24AB, the two terms are color-coded for easy tracking. Now that square root on the right side, when simplified, is a clean number 3 halves. So since half the sum is at least 3 halves, then the sum of those two special terms is at least 3. So then we have the following as lower bound, 1 plus 9 fourths plus 3, which is 25 over 4. Now, the problem asks specifically for the sum of the numerator and the denominator, so that's 29, which is letter A. But wait, is 25 over 4 really attained? In the AM-GM application, is 3 halves attained? Well, equality occurs when the blue and red terms are equal. And does this condition happen? Well, it does when a squared b squared is equal to 1 over 54 times 24. Now, there are many ways that this can happen. Like, for example, when a is equal to 1 over the square root of 54 and b is equal to 1 over the square root of 24. There are infinitely many ways where the condition for equality will happen, but the fact is, equality can indeed happen. So, yes, 25 over 4 is truly the minimum of the given product. However, is checking whether equality happens, is this really necessary? Let's have a look at a different approach to the problem. Don't forget what we got from our previous solution. The minimum is 25 over 4, which for purposes of comparison, I'd like to point out is 6 and 1/4. So we're still interested in the product of these two factors, the gold factor and the purple factor. Now, each factor is a sum. What would happen if we were to apply the AM-GM inequality on each of these two factors? Now, half the gold expression, this is an arithmetic mean. This should be at least the geometric mean of 18a and 1 over 3b, which is the square root of 6a over b. Similarly, half the purple expression is at least the geometric mean of 3b and 1 over 8a, which is the square root of 3b over 8a. Thus, Go back to the first line. The product of the gold and purple factors is at least twice the square root of 6a over b times twice the square root of 3b over 8a. The a's and b's disappear when you do the multiplication, and we get as product 6. So, okay, the product is greater than or equal to 6. Does this not contradict the solution earlier where the minimum we got was 6 and 1/4? So, is 6 the minimum? Can 6 be attained? Can equality occur? In our first application of AM-GM, equality occurs when 18a is equal to 1 over 3b, which happens when ab is equal to 1 over 54. In the second application of the AM-GM inequality, well, equality happens when 3b equals 1 over 8a, which occurs when ab is equal to 1 over 24. But observe that these two conditions for equality are incompatible. If AB is equal to 1 over 54, then okay, the gold term reaches its minimum, but the purple term doesn't. It's the same situation when AB is equal to 1 over 24. The purple term reaches its minimum, but not the gold term. So the purple and gold terms, they reach their respective minima, but for different pairs of values of A and B. So therefore, the product 6 that we got earlier, that's actually never going to be attained. So that means 6 is not the minimum because it's never reached. So what's the lesson here? It's that it is always worth checking whether the minimum or maximum is actually attained. Now let's have a look at this next problem from the 19th PMO qualifying stage. If b is greater than 1, find the minimum value of 9b squared minus 18b plus 13 divided by b minus 1. The condition is that b is greater than 1, and in the expression, the denominator is b minus 1. So when I tried out this problem, I thought of replacing b minus 1 by, say, t, so that instead of requiring b to be greater than 1, equivalently, we can require t to be greater than 0, which for me is a simpler condition. And also in the given expression, the denominator b minus 1 becomes t, and in the numerator, all occurrences of b can be replaced by t plus 1. You can verify the algebra. I'll skip the details, but this is going to turn out into a really, really nice and simple expression. 9t squared plus 4 over t, or 9t plus 4 over t. So what we want to do is to minimize the sum, where we see that if we happen to multiply 9t and 4 over t, this is going to clean up rather well when we get their product. So let's apply the AM-GM inequality. Half the sum of 9t and 4 over t, that's their arithmetic mean, is at least their geometric mean. The product of 9t and 4 over t, then you take the square root, the t's cancel, we get 6. Thus, the sum of 9t plus 4 over t is at least twice 6, which is 12. And therefore, the answer is C. And you know the drill. Does equality actually occur? Yes, when 9t is equal to 4 over t. Initially, you're going to get two different values for t because you'll get a quadratic equation. But hey, t is positive, and so equality occurs when t is equal to 2/3, or because b is t plus 1. So equality occurs when b is equal to 4/3. And then here is the last PMO problem that we're going to solve in this video. This is from the 22nd Philippine Math Olympiad qualifying stage. Find the minimum value of 7x squared minus 2xy plus 3y squared all over x squared minus y squared if x and y are positive real numbers such that x is bigger than y. That's the last problem, by the way, number 30. The conditions are given for a reason, so we need to see how they come into play. Since x is bigger than y, I thought of writing x as y plus k. If we replace all occurrences of x by this, that's going to lead to an expression in terms only of y and k. And the requirements would therefore have to be maintained just for y and k. And we get a nicer pair of requirements, which is that y and k have to be both positive. So I think this is a simpler set of requirements. So let's see what's going to happen. Let's do the algebra, or rather, at least you can check it out, do it on your own. But after all the simplification is done, this is what it's going to turn out to be: 8y squared plus 12yk plus 7k squared all over 2yk plus k squared. So just do the algebra to verify. Now, um, what some of us might notice is that the three terms in the numerator and the two terms in the denominator, all of them have degree 2. And something nice happens when we divide both the numerator and denominator by k squared. This is what we're going to get. In the numerator's first term, 8y squared over k squared, or 8 times the square of y over k. And then 12yk divided by k squared, that's going to be 12 y over k, 12 times y over k, and then continuing plus 7 in the numerator, and then in the denominator twice y over k plus 1. Now, what we notice is that all the y and k that we see here can be found only in these fractions y over k, suggesting one more substitution. Let t be equal to y over k. And because y and k are positive, this just means that t must be positive. And the substitution leads to the following: 8t squared plus 12t plus 7 all over 2t plus 1. Definitely much simpler. It's just in terms of one variable with one requirement, which is that t has to be positive. We want to find the minimum of this. Now, does this fraction remind you of the expression we had to minimize in the previous problem? Doing the actual division gives us 4t plus 4 plus 3 over 2t plus 1. However, if we treat 4t plus 4 as a term and 3 over 2t plus 1 as the second term, if we multiply them, because that's something that's going to be found in the geometric mean, the product's not going to be nice. And that's because 4t plus 4 is not a multiple of 2t plus 1. But you know what is divisible by 2t plus 1 and close enough to 4t plus 4? It's 4t plus 2. So we can split 4t plus 4 as 4t plus 2, and then plus 2, let's move it all the way to the end, giving us the following. Oops. Twice 2t plus 1, that's 4t plus 2, and then plus 3 over 2t plus 1. So something nice going to happen here. So let's highlight that in gold font. And then plus 2, let's have it weight at the sidelines. Let's apply the AM-GM inequality on the sum in gold. Half of this is at least the geometric mean. And that geometric mean is the square root of twice 2t plus 1 times 3 over 2t plus 1. The 2t plus 1's cancel out, and that's going to be the square root of 6. Half the sum in gold is at least the square root of 6. So therefore, going back, the sum in gold is at least twice the square root of 6. And then don't forget the plus 2 there. So is equality achieved? Well, yes. When twice 2t plus 1 equals 3 over 2t plus 1, and because t is positive, so 2t plus 1 is positive, that actually means 2t plus 1 is equal to the square root of 3 over 2. It's not really necessary to solve for t since it's clear this has a positive solution for t. So yes, indeed, the final answer, the minimum value of the expression, is twice the square root of 6 plus 2. Now, that's already a lot of problems for this video, but you may have observed that all our examples asked us to find the minimum of something. The AM-GM inequality can also be used to find maximum values. For example, let's consider this illustration. Find the largest possible area of a rectangle having perimeter 40. If the dimensions are L and W for length and width, then the area A equal to LW, what can we place as an upper bound for it? The perimeter is 40, so twice L plus W equals this perimeter, which means L plus W is equal to 20. So we know what the sum of L and W is, and we want to see how large your product can be, and the sum and product appear in the AM-GM inequality. In the arithmetic mean, the sum L plus W in the numerator is 20, and on the other hand, the geometric mean on the right is the square root of the area A. So on the left side, that's going to be 10, and then square both sides. Consequently, A is at most 100. Does the area reach 100? Well, equality occurs when L is equal to W, or in other words, when the rectangle is a square. So, yes, equality is possible, and the largest possible area is equal to 100. So, you can check. If you have a square and the perimeter is 40, that means the length of each side is 10, and the area is indeed 100. Note that all we have applied in this video tutorial is the simplest version of the arithmetic mean geometric mean inequality, where we compared the AM and the GM of two non-negative numbers. What if we have three or more numbers? It turns out that we can extend the AM-GM inequality to more terms involved, but that can be the topic of another video in the future. So thanks, and I hope you learned something new from this video. Bye-bye.